this class is a follow-up on the previous class, even though this is not exactly week one, but we're going to have to jump from this point. So for today, the learning objectives are a few. One of them is we want to explain what data science is and how it differs from analytics, AI, machine learning, and deep learning. We want to describe the key roles in modern data ecosystem. So in a typical data science team, what are the kind of professionals that you see working in those teams, and what exactly is it that they do? We want to explain the data science life cycle and why it is iterative, why it's a continuous and ongoing process. And then we want to frame vague business questions into a data ready and analytics question. Sometimes you typically have a business problem. The issue is, how do you frame that problem properly so that you'll be able to set it up for success once you want to apply data science tools? Because that background is really, really very important. And a lot of times you need domain level expertise to be able to correctly frame a problem. And then eventually we're going to use Python, Pandas, and Matplotlib to conduct our first data science analysis. And we would interpret the outputs, with evidence, caution, and then context so that you can understand the results of those analyses. And then we can eventually identify a possible capstone problem area, which is something you guys will begin to think about. So as we continue in the class, I need you to begin to think about what possible projects you are also going to do, because that would be one of the um, requirements or outputs of the course eventually. So as you see the way we frame a typical data science problem today, I want you to begin to think of a hypothetical problem, right, that you are going to work on, that you would eventually present to the group.
My personal person. My personal person.
Àwọn lẹ̀ ń gbà ẹ̀wọ́ lẹ̀ ń gbà mí.
Mo rò pé bóyá no torí pé ibi tí mo wà ẹ mọ̀ gbé bàrí àti wà láàrin wa.
Bàbá yín mo lò. Omi.
So sorry about that. So what is data science? Essentially, data science is an interdisciplinary discipline that uses data, computation, statistics, and domain knowledge and communication to generate insight and support decisions. So as you can see, data science is not one arbitrary domain. It's actually an intersection of multiple domains. When you think of it like your high school math, where you have a Venn diagram, right, with several circles, and some of these circles intersect somewhere in the middle, that's how data science essentially is. And it's essentially an intersection of data, the field of data, computation, which is a lot of computer science, programming, and all of that, some statistics, and then there is usually domain expertise or domain knowledge, because data science is a field that essentially tries to solve problem in almost any conceivable human domain where there is some kind of data, right? So domain expertise has to do with you, for specific people in that domain, having the domain experience, knowing things about that domain, the ins and outs, and essentially how that domain works. That kind of knowledge is really very important in framing a data science problem. And of course, the ability to communicate, right? So once you have your results, you need to be able to communicate it, depending on what kind of stakeholders, in a very intelligent way that it can make sense to your stakeholder, and hopefully it's properly framed to be able to lead to some kind of action in the future. And the idea is to generate insight and support decision making. So once you have a data science problem, you frame it correctly, you do the necessary work. The idea is, at the end of the day, it should be able to generate some kind of instant insight. And better still, it needs to lead to some kind of decision making. So it can help you make decisions. And sometimes these decisions lead to cost savings, it needs to productivity, it needs to income growth and all kinds of things. So it could lead to mitigation of risk, it could lead to all kinds of really positive things. So a practical definition of data science is the disciplined, and that word disciplined is actually really very important. It's a disciplined, in other words, it's really structured, but it's a very disciplined process of turning data into insight, prediction, explanation, or action. So that is essentially what data science is. And it is valuable because organizations really need data, rarely need data by itself. Even though they generate data, they rarely need it. They need better decisions and earlier warnings. That's exactly what organizations have: clearer explanations, informed processes, and measurable outcomes. So these are all the kind of things, even though organizations sometimes have data, but data doesn't really mean anything. What organizations are looking for is, how do we mine that data and get useful information? Think of it like crude oil. You can have all the crude oil you have in the world. That is not helpful to a motorist, right? It's not helpful to families. The only time those things become crude oil becomes helpful is when you have extracted the different fractions from it, right? And now you have bitumen that you can use for roads, you have diesel that you can use for trucks, and you have petrol that you can use for cars, and you have like the JP8 that you use for planes, and then you have wax, you have all kinds of things, right? But that doesn't happen until you've been able to go through some kind of fractional distillation of the crude to get all of these other derivatives. That's the way it is exactly with data. So in the case of data, it's very, very important for us to have the data. In the case of data science, it's very, very important for us to have the data, but then we need to go through some kind of fractional distillation process. And that process is actually going to be very disciplined, because that's the only way you can actually calibrate to be able to get different kinds of outputs, right, for the specific needs of your various stakeholders. So now looking at data science, analytics, AI, machine learning, and deep learning, these are sometimes some of these are used interchangeably, or some are subsets of others and all of that. But let's essentially look at one way to look at each of these disciplines. So data analytics, the primary question that data analytics is trying to solve is what happened and why, right? So at the end of the day, some of the outputs you get is reports, dashboards, and insights. So, and a lot of times in data analytics, what you're doing is you already have historical data from the past. You get that data and you're trying to query from that data what actually happened and why did it happen, right? So you run analysis and all of that, and then you develop dashboards that try to describe that problem. So a lot of times data analytics actually lives in the realm of prescriptive descriptive analytics, where you're essentially trying to understand what happened to describe it, right? And then you have data science. And the question is trying to answer is, how can data support decision making end to end? So that means what we are trying to typically get as an output is, we want to find insights, we want to develop models, and we want to be able to make recommendations. So often data science will probably start with, there are elements of descriptive analytics, which is in the domain of data analytics. And then eventually you begin to build out models. And often data science looks more into the aspects of predictive and prescriptive analytics, right? Because what you're trying to do is you want to be able to, based on historical data, right, create models that can help you predict the future, right? And also prescribe solutions, right? So we're essentially looking for insights, and then we want to be able to say hey, this is what's going to happen, which is why if you look at machine learning, that's why I said sometimes some of these things are subsets of each other. Machine learning is a fundamental tool that is also used in data science, right? So you can see the what question it's trying to ask is, can an algorithm learn patterns from data? And a lot of data scientists actually develop machine learning models, right, to be able to learn those patterns, to make predictions, classifications, to build out clusters, with a a goal of arriving at some kind of model, getting insights and making predictions. So kind of data science, machine learning, artificial intelligence, deep learning, all of these actually essentially feed back into data science. So if you asked me to actually classify these things, I would classify them more into data analytics and data science. Data analytics, where you look at historical data and try to make sense of that data and describe what's happening through that data. And data science is where you absorb a lot of things happening in data analytics. That's why it's said how can data support decision making end to end. So you start with the descriptive part, and then you apply machine learning tools, artificial intelligence, and deep learning tools. All of these three are tools. So machine learning, for example, is a subset of artificial intelligence, and deep learning is a special type of machine learning. But all three of these, right, are tools essentially that you can put together, right, in trying to solve data science problems. So analytics is trying to answer the question, can a system perform tasks associated with intelligence? Automated reasoning, recommendation, and agents. And deep learning has to do with neural networks. How can they learn complex representations like image, text, and all of that? Again, all three of these, frankly, in my own estimation, are all tools that you apply in the data science field to try to solve the problem of prediction and prescription of solutions based on the available data data that's available to you. And in the course of this course, we're actually going to do a little deep dive into artificial intelligence, machine learning, and deep learning, because they are vital tools for a data scientist. So in summary, the important thing is to look at data science, right, in two main areas: data analytics, where you're looking at historical data, and you're trying to describe what has happened and make sense of it. And data science, which essentially takes a bit of descriptive analytics and then goes further into predictive analytics and prescriptive analytics. Predictive analytics has to do with building models and then using those models to predict what would happen next, while prescriptive analytics builds on what has been predicted and makes recommendations, right, to the right stakeholders about how to respond to what has happened. So he said this course starts with core analytics and data science workflows and introduces machine learning and deep learning later. So it's an end-to-end thing. So for the key roles in data science, you're going to see a data analyst, right? And the goal of the data analyst, as you can see, data analysts tend to work in the field of data analytics. They summarize and communicate patterns. And some of the tools they use is Excel, SQL, Power BI, Tableau, and Pandas. And then data scientists, they build analytical and predictive models. And these are some of the tools they use. We're going to use some of these tools. And then you have a data engineer. So what a data engineer does is actually to build reliable data pipelines, right? How can I have different stages in this process. How can I build a pipeline so that data can flow seamlessly through each of those processes? And the way some of the tools you use are SQL, Spark, Airflow, cloud platforms, and all of that. So you want to build that platform. Think of it like you want to get water to a 10th floor of a building. How do we get water to the 10th floor of a building? You have to build pipes, right? And the connections and the pumps and all of that. while water is the data, the pipeline that you're building to get water to where it's supposed to go, like your plumbing framework, that's what the data engineer essentially builds. So the tanks to store the water, the pipes to flow the water, and as that water is flowing, you see a drop in pressure, and you want to put pumps at pumping locations or stations to make sure that that water is flowing and is distributed. But the data scientist needs that water maybe on the 10th floor to be able to run analysis, build models and all of that, and then distribute it all over the building. That's kind of the relationship between the data scientist and the engineer. And then that's where you now have machine learning engineer. After a data scientist has built the model, you want to be able to productize that model in order to put it into production. And that's where the machine learning engineer comes in. So works hand in glove with the data scientist to make sure that we operationalize that model that's been built. So think of the data scientists as like the guy in the lab building out things, while the machine learning engineer is like the production engineer after everything has been built, quality tested and everything. We can now make it available to a larger audience to use that, right? And that's where they're using API, where you do API calls. You're using Docker, you're using machine learning flow and CI/CD. And then finally, we have the analytics translator, right? And this is the person that tells the story, the communication experts. They connect business needs to the technical team, stakeholder analysis, storytelling, and requirements. That's where the analytics translator is. So in real projects, these roles overlap. In some cases, as we mentioned, because there are, for example, you see the data scientist and the machine learning engineer. Depending on how big the team is, sometimes the data science might be doing the job of a data engineer and a machine learning engineer. So it depends on how big and how robust the team is. Even in very big and robust teams, sometimes the handoff is very smooth. So which means that sometimes your functions might overlap. It's just an internal thing for the team to decide how things overlap without conflicts. So thinking of the data science lifecycle, a couple of things. The life cycle can be, set up or organized in all kinds of ways. But for this particular class, we've kind of set it up in like 8 different steps. So the life cycle of a typical project's data science project will go from, first of all, the decision problem definition. You want to know what exactly it is that you're trying to achieve. Because you can't solve all of the problem. You have to be very specific about your problem, because if you're not very specific about the problem you're trying to solve, when you eventually get a result, you might not even know you have gotten a result, right? So I know last week I talked a little about problem definition. You can't be vague with your problem definition. So after that, it's only after you have accurately calibrated what the problem is that you are able to now to know what specific data you might want to gather. Some companies just start gathering data, right? And they have tons of data, terabytes of data stored all over the place. And then now you're trying to solve a data science problem. In some cases, they bring in a data science team, and they ask for what kind of data they have, and they now realize, even though they've been collecting data for 5 years, the data they have isn't enough, the type of data that is required to answer the problem they are trying to solve. So in that case, maybe they might have to start collecting data afresh and give it some time to generate enough data that would make sense in building out the project. So the point is, just having data is not enough. You have to be able to have data, the actual data that is needed, and it has to be data that is available, because if availability is a problem, then answering that question might be difficult. There is also an issue about the legality of data, because you can't just use any kind of data. In some cases, especially personally identified information, you have to scrub it. depersonalize it, and then sometimes the data might not be ethical. So you want to make sure that the data you are collecting, is first of all needed, it's also available, it is legal, and it is ethical to use that data. And then you have the data preparation where you now begin to clean that data, transform that data, engineer, combine. There are all kinds of things that you can do with data. Often that's the part of the data science lifecycle that takes the most time, right? Trying to prepare that data. Sometimes you have things that are missing in the data, or people have entered the wrong information, and the wrong information is so obvious. So you want to remove all of those, right? So when something is removed from where data is supposed to be, how do you fill it up? Those are all the kind of questions that we would answer in the later part of this course. And then after that, you do go into exploratory data analysis. Again, that looks like what we do in data analytics. So we call this EDA, exploratory data analytics, where you begin to check out that data to see what that data actually contains. So for example, if I'm using an Excel sheet that is, I don't know how many rows an Excel sheet can take, but hypothetically, let me just say it's 200,000 lines. It wouldn't be easy for me to scroll through the whole 200,000 lines to figure out all of the things. But I can literally, in doing my exploratory data analytics, I can write a line of code where I ask it, so how many columns do I have? How many rows do I have, right? How many, all kinds of things. I can do that. So even without going through all of that data, I can quickly query that data to have a sense of what that data looks like. And that's what you do in exploratory data analytics, right? So you want to find out the patterns, the anomalies, the relationships, and all of that. So after that, that's when you go into modeling analytics. Modeling analysis, right? That's when you begin to try to figure out what methods do we actually need to be able to that would fit the question and then the data. That's the next step. And after that, we want to begin to look at how good, reliable, or useful are the results. I've used these particular tools, I've built out these models. So how good are these models, right? How accurate are they, and all of that. And if talking of the process being iterative, if I come in there and I see that the models have developed, don't answer the question, or they answer the question, but the accuracy is really, really very poor, that's where I go back to modeling and analysis to go try other models, right? And look for other tools, methods, or models, right? To be able to answer the question. So I go back and forth between 5 and 6 until I get something that's really good, is reliable, and is useful, and it does answer that question. Once I have that, then the next thing I want to do is to now communicate that problem, because a lot of times if you get an answer and you don't communicate it, then it's hidden in a book, or it's hidden somewhere, you can't take action, it doesn't bring any insight, and it can't inform decision making. So often, especially in companies, you want to be able to now create a summary of what you have done. So I mean, you might have a whole report about this whole thing that is 200 or 300 pages. Nobody is going to read your 200 or 300 pages. Sometimes you can just use one slide to communicate everything that is in those 200 pages, right? But you need to be skilled in the very act to be able to know how to communicate that information. Or it could be a slide deck, 5 to 12 pages of a deck, right? Where you can communicate all of that information, often with charts, with all kinds of representational artifacts, right? You can communicate all of that in a very short time to your audience, and that's where communication becomes very, very important. And of course, as you can see, you have to focus on what the audience needs to know and what they need to do. That's the job, one of those things in the life cycle process. And then, of course, you have the deployment and monitoring. How will the insight or model be used over time? sometimes you have to deploy it so that people can query the result from time to time. You have to make that decision. How do we monitor it? At some point, that model might not reflect the current reality. And in those cases, you have to go get new data, right? Let's say you are in a business environment and the trends have changed. Your model was based on the previous trends, right? And then now all of a sudden it's not going to be accurate anymore. You want to go out there, gather more data, and then you update your model, so that it reflects what's happening at the current time, and that's how you keep up with the accuracy of your system. So when it comes to analytical thinking, there are four key pillars, right? You want to frame the problem clearly, which is what I talked about, one of those things we talked about, because poor framing creates wasted analysis. Why are the sales down? You can't ask a question like that. Why are the sales down? That's too vague. Something more specific will be like which customer segment has reduced purchase over the past 3 months. So you can see you are specific, right? It's not about sales being down, but it's possible that sales is down, but let's say you have 10 locations, right? You want to dig deep into that data, and that's where you do your exploratory data analytics to find out what's happening. Once you find out what's happening, you might find out that 8 of the locations are doing very, very well, excellent, maybe performing better than they were last year. And you can see that there are two locations that are dragging sales down. Now, instead of trying to ask yourself, why are the sales down? That doesn't make sense. After doing your exploratory analysis, that's where you now go to those two and focus on those two, right? So the question you might be asking is which particular locations, for example, have reduced sales? And you can find that from an exploratory analysis, and then you can dig deep into that. And then maybe if you look at it very well, this only happened within the last 3 months. And with exploratory data analytics, you can find that out. And then after that, you now zoom in. Once you find that it's those two areas and it had happened over the 3 months period, that's when you can now zoom in and try to figure out what's happening. Instead of analyzing all of the data, you want to now pick that data and then begin to dig deeper. So the next thing is you want to use appropriate techniques based on data and context. Like I mentioned, once you do your EDA, then you can now focus on the specific area, and then you begin to ask yourself, what tools? One problem a lot of people have, especially engineers, is to just see a problem, jump right into it and bring out their tools, specific tools. You have to understand the problem first before you decide what tools are going to be used. Then after that, you need to interpret the results with critical insight. Numbers do not speak for themselves. Analysts translate outputs into evidence-based meaning, right? So just because you got data is going to be staring you in the face, right? But you need someone that really understands that data, because you can have data and have two people interpret it differently, which is why you need someone that really understands the context, understands the domain to be able to interpret what that data is saying, and then to also have, the insights to be able to recommend to stakeholders what to do with the outcome of that data. And then finally, we have the aspect about iterate and improve. Like I mentioned, you have to iterate, because sometimes you might get something and the results doesn't really look good. You go back. So it's not a linear process where you go from stage 1 to 8. In the life cycle, sometimes you have to go back and redo step 4, come to 5, come to 6. And after the evaluation, it doesn't look good, you go back. So it's an iterative process. So talking of this, I'm going to start first of all by giving us what will typically look like, what happens in your Jupyter notebook when you're trying to load up, a data science problem. There are a couple of tools that you need to use, and it'll be nice for you to go look at these, for example, some of these libraries. after you've loaded up, you see import numpy. Numpy is one of the libraries for dealing with numbers. Pandas is one of those for structuring your data, and then you set all of this up. Here is telling you how to set up. Now, remember your pandas. So for each of these, so for numpy, we are loading it as NP. In other words, anywhere you see MP, you're actually referring to numpy. And then for pandas, anywhere you see pandas, PD, you are referring to pandas. That's your way of saying this is a shortcut to it. And matplotlib, which is usually used for diagrams, it's like a package that is used for diagrams. Anywhere you see anywhere you see PLT, essentially that is your matplotlib. So one way to look at this is literally like your Windows, right? If you set up your Windows operating system, but there are different packages inside of it. So this is essentially like Python. Let's assume that Python is like your operating system, but there are and that operating system has some inbuilt packages. So Windows has Notepad, it has some other things, but it doesn't have your MS Team. It doesn't have your Excel and all of that. You have to install a Microsoft package, right? So one of these could be your Microsoft package, and maybe there's some other thing you want to do, and that's your package, and these are all your package. So you've installed all of those, right? And then you set up your environment. This, of course, is print, you know, um, and then in some cases, you want to randomize data, and this is what you use to randomize that data. And then these are your print options. If everything works well, I want you to print that the environment is ready. And I need you to say, pandas. I need you to tell us the version of pandas we are using. I need us to tell me the version of numpy I'm using, just like you're asking, are you using, Microsoft, what version of Microsoft and all of that. So we run all of that. You can see it's printed out everything. Our environment is ready. We're using pandas 2.3.3 and we're using numpy 2.3.5. So this is a problem that we are going to try to solve using after we've loaded this, right? This needs to be loaded before we can start. This is essentially like opening your Word document, opening your Excel document. Everything is ready before we can now start using those tools. Look at a practical scenario. So a company believes sales are declining. That's the business concern. Now, for you to frame that problem, a typical way to frame it, a lazy way, frankly, I would say for framing it is, why are sales down? Well, good question to ask, but that's not a really good question if you're trying to solve a problem of this nature. A better framing will be, which regions or customer segments show the weakest month-over-month sales decline, and what factors might explain this change? That is more specific. So of course, as in all other things, right? If we want to do this, we want to be able to get the sales data. How did the company perform? We can create a small data set to practice analysis of a problem like this. The goal is not to prove a final conclusion. The goal is to practice disciplined reasoning. So that's why we're trying to do this. So let's say we load up that data, right? That would be, different columns, for example. We have your customer ID, you have your region, you have your segment, blah, blah, blah. We load all of this up using your pandas data frame. In other words, we are trying to create a data frame from this data, right? And then one of the things we want to say is, for this, your sales, we want to find out the change in sales. To get the change in sales, we are adding one additional column. The change in sales will be the sales of this month's sales. We have this month's sales here. This is our month sales minus last month's sales. We want to subtract it. In other words, we are creating an additional column, which is a derivative of these two columns, right? And then the next one we want to find out, we want to see the percentage change in the sales between the 2 months, which is the sales change, which is this, divided by last month's sales multiplied by 100%, and then that will give us our sales, right? So that no, so plus this, then we want it to print out sales for us, which is all of this, everything here, right? So if we run that, this is what you get. In other words, you see our customer ID, if you look at it, 101, 102, that's what we have here. It's laid that out using this as our column, these are our rows. The regions, north, south, east, blah, 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 we have all of that here. The segment, enterprise, SB, SMB, SMB, enterprise, SMB, blah, blah, blah. So it shows the various segments. And then last month sales, this month sales, the change, in other words, 200 minus 180, which is what you have here. 150 minus this, minus 50, blah, blah, blah. And then we take a percentage of it. And this is how we got the percentage. And all of a sudden, this is what we get. All right. So you can see all the percentage drops. So in these 2 months, we have these drops, 40% drop, in this region, blah, blah, blah. So to do our first inspection, what we want to do is we want to run, we want to know the shape of the data. In other words, it's trying to see how many columns, how many rows, and all of that. That's what your kind of shape is usually, and you want to find out the number of columns, the data types, what the data, the missing values, all kinds of things, right? And then if we run all of this, and that's your EDA, you're literally finding all kinds of, these are the columns, right? Because the first one where it's asking about columns, this is all of the columns. The data types, it was asking about data types. Each of them, the customer ID is in 64. Region is an object, segment is an object in 24. All of that percentage is a float. You can see a float 0.000. So that's what a float is. The missing values, you're trying to check if there is any missing value. You can see there's no missing value here. If there was missing value, it will show you which of the values are missing. So we want to also describe the data, and to describe the sales data generally, right? This is what we have. So to describe that data, if you look at it, that's what we have. So it's checking all kinds of things. Customer ID, right? How many IDs do you have? You have 8 of them, right? How many regions? You have 8 regions. How many segments? If you go count all of this, you see number of segments, how many regions, and all of that. This month sales, there are 8 percentage, blah, blah, blah. Are there any unique data for the region? Yes, because the unique ones are 4. Where is it? Yeah, there are only 4 unique regions. Some are repeated, like north, north, that's 1. South, south, that's 1. East, that's 1. And west, those are the 4 repetitions. So all of that, that's what you have. So now the interpretation prompt, right? You want to answer briefly, what is the unit of observation in this data? What fields are categorical? What fields are numerical? What important context is missing from the data? These are some of the things that you need to answer. So descriptive analytics. Now, descriptive analytics summarizes what happened. We begin by examining sales change by region and segment. So by using a method like this, right? Dot group by, right? We want to group everything by regions, and then we aggregate by this. If you run this, for example, that's how we end up with this, right? So south, the last month sales, because we are trying to aggregate all of it around the regions. So if we aggregate by regions using this code, that's what we get. So all through the south, if you look at this now, you're seeing that where our problem is arising is from the south, right? Because the percentage change is 36%. So this north and south are not doing very well. The problem is not with the east or the west, right? And it all depends on how you have benched it. Are you trying to say that a 2% increase is okay? If a 2% increase is not okay, then you might want to begin to look at this too. But for now, if all we're trying to figure out is what is dragging us down, you can see is the south and the north. That are the two areas that are dragging us down, all right? So if we decide to group by segment, we run it by segment, you can see the total change here is minus 55, total change, enterprise as and SMB, those two areas, things are not going very well. The percentage change here is also not good. So if we decide to do a visualization of all of this is what we see, total sales change by region. And then if you total change in sales, total change by region. So you can see the north and the south. We already saw this before. These are the areas that are pulling us down. This is worse. So if I wanted to go present this data, right, I probably wouldn't bring something like this to an executive presentation. I would provide this because by just looking at this, and this is where we talk about the presentation, right? By just looking at this, we are able to immediately look at that, this diagram, and then we can tell. So next thing, we want to also look at sales change, last month sales versus month over month change. If you run that, you can see the west doing well, east above, and then this is over last month sales, right? You see all of that. So then we are talking about technique selection, descriptive, diagnostic, predictive, and prescriptive. Remember, I kept using those terms. What exactly are they? Descriptive is trying to answer the question, what happened? Sales declined in the South region. Diagnostic, why did it happen? Decline may be related to few repeats purchases. Predictive, I'm trying to predict what could possibly happen next. What might happen next? We estimate next month's sales or churn risk, right? And then prescriptive, what should we do? Recommend retention campaign for high risk customers. So if we're expecting that churn is going to happen based on our prediction, that we can have targeted outreach, right? Or some kind of retention campaign to especially targeted at our high risk customers, right? To make sure they don't drop off the wagon. So that's essentially an example of how to go about this. So some common mistakes, right, people make is, for example, coding before defining the problem. True, because the little sample that you pick up might end up not actually being representative of what's happening. So you want to make sure you have enough data, or reporting a chart without examining what it means. Pretty obvious. You do an EDA, you see a little result, and then you just put it out there and you act like it's gospel. You don't want to do that. Or there's some missing context, assumption, or limitations. You have to, because sometimes when something is happening, if you don't gather the whole picture as at why it's happening, all of a sudden you might miss what's actually happening. or you want to confuse correlation with causation, that right there is a cardinal sin in statistics. Just because something is happening doesn't mean two things are happening, doesn't mean that they are necessarily related. Okay, if A moves and then B moves, that doesn't necessarily mean that A is moving because of B. They might be moving randomly on their own. But that's what you want to figure out. Forgetting that the audience needs a decision ready story. You know, there's no, you have all these things, and then after your presentation, everything is nice, but that's your presentation isn't leading, is not providing clarity as to what needs to be done next. If you haven't gotten to that point where you have some answers about what needs to be done next, you probably need to go back to the drawing table. So for the the next thing we are going to have here is analyzing student performance. So look at this question, right? Use the data below to analyze student performance, right? What patterns appear to be associated with final exam performance, right? We do the same thing where we are trying to build a data frame, and this is all the data. And then first of all, we build it. You create the table, right? If you look at it, it's nicer to look here. So you have all these students. These are their IDs. These students, their ID is S1, S2, S3, S4, S5. The number of hours they have studied, maybe for a typical exam, this guy studied 5 hours, 8 hours, this person studied for only 3 hours, this studied for 10 hours, this studied for their attendance rate. 80% of the time this person was in class, this person attended 95% of the time. This guy that studied for 3 hours also wasn't coming to class, was there 65% of the time. The one that studied for 10 hours came 98% of the time, and all of that. Look at their score. After they submitted the assignment, this is the score that they had. Then they had their quizzes and then their final exam. So these all three are, the outputs, right, in terms of results. So we want to kind of print out the information about the students. That's students.info. If you run that, and then that's how you have all of this, right? And then we come here. We want to describe what's happening with the students, general description of everything that's happening, their results and all of that. So when we look at their study hours, each of them, all 10 of them contributed something. The average in terms of the average number of hours they studied is 6.5, attendance rate overall, assignment score, that's the average score of everyone, the standard deviation for the scores, the minimum 25 percentile, 50th percentile, 75th percentile, then the maximum for each of those, the maximum scores, and then we plot it, right? And essentially what we are plotting is their final exam score versus the the number of hours they studied versus their final exam score. You can see for those that studied, for 4 hours, their result was something like this. So it's almost linear. It almost feels like the more hours you study, the higher your exam score. That's what this is showing. And then now we want to add something. The average score is equal to the student's assignment score plus, their quiz score, their final score. We take the mean of all of that, and then we sort all of that. And then at the end of the day, this is what we have. So these are their average scores, So that would be it. And this is an assignment, something you can go try out yourself. So you create a short Jupyter notebook that includes a clear analytic question, a small data set, data inspection, summary statistics, 2 visualizations, 3 written insights, 1 limitation, and 1 possible capstone project. So essentially, your notebook should tell a story, not merely run code. That will be, the first thing I want you to begin to look at for this week 1. So I'm going to temporarily stop here and we'll take a little break.